Okay, perfect. What's the original function? The original function here is e to the radical x. E to the radical x. Okay. Okay, so we could say u is equal to u, and dv is equal to, or u is equal to 2u basically. Let's do 2u. Okay. Again, I could do a change of variable if I want to. Maybe we'll do a w here instead of a u. Okay, because we've already used u. Can you pull out the 2? Sure, you can put it out in front if you wanted to. That's fine. Okay. If you want to do that, we can do it that way. It's fine. 2 times u e to the u du. Okay, so let's do w is equal to u, right? Okay, and then dv is equal to e to the u du, right? So v is equal to e to the u. Okay, dw is equal to du. Okay, so what are we going to get here? We're going to get this guy and this guy. Okay, so we're going to go 2 times u e to the u minus the integral of e to the u du. Okay. Okay. So what is integral u to u? Well, it's just itself, right? So this is u e to the u minus e to the u, right? All times 2 plus c. Okay. So this is going to be 2u e to the u minus 2 e to the u plus c. And now we just have to sub back in for what u was. What was u? It was radical x, right? 2 radical x e to the radical x minus 2 e to the radical x. Okay, and if I really wanted to, I could factor out, I didn't have to multiply it out. I could factor it out. It doesn't matter. We could leave it like this, or we could factor out what they have in common, and that's 2 e to the radical x times radical x minus 1 plus c. Okay, so either way is fine. Okay, let's go over number 3 here. Let me change pens. Okay, number 3. Okay, let's integrate. Okay, x to the 5th plus 1 over, oops, didn't mean to open that. Okay, x to the 5th plus 1 over x cubed minus 3x squared minus 10x, okay, dx. Okay. Okay, I'll be right back. I'm going to get something to drink. I'll be right back.
Professor, would that be a long division or no?
Yes, this would be long division. So let's do that. Okay. Okay. So let's do x cubed minus 3x squared minus 10x. Okay, plus 0. Okay, all into, okay, x to the 5th plus 0x to the fourth plus 0x cubed plus 0x squared plus 0x plus 1. Okay, let's do long division here. Okay, x cubed goes into x to the fifth, x squared times. So let's go x squared here. X squared times x to the cubed is x to the fifth. This is going to be minus 3x to the fourth. Okay, this is going to be minus 10x cubed. Okay, and then plus 0x squared. Okay, and now I want to subtract, which is changing the sign and adding. Okay, so this becomes 3x to the fourth. Okay, plus 10x cubed. Okay, plus 0x squared. Okay, and I bring this guy down as well, plus 0x. Okay, so now we're going to plug in an x. Okay, plus x. No, sorry, plus 3x. Because what times x cubed is 3x to the fourth? It is 3x. Okay. So 3x times x cubed is 3x to the fourth. 3x times negative 3x squared is negative 9 x cubed. Okay, and then 3x times negative 10x is negative 30x squared. Okay, and then we get 0x. Okay, as well. Okay, so again, change the sign and add. So minus, plus, plus, minus. Okay, that cancels. This becomes 19x cubed. Oops. 19x cubed. This is going to be 3x times, this is going to be plus 30x squared plus 0x, and then you could bring down the 1 if we wanted to. Do you want to do that yet? Yeah, that's fine. 0x plus 1. Yeah, that's fine. We could bring down the 1. Okay, so let's bring down the 1. Okay, so now this is going to go in 19 times, plus 19. Okay, 19 times that, it's just going to be the same thing that we had before. 19 x cubed. Okay, this is going to be 57. Okay, minus 57 x squared. Okay, plus, no, sorry, minus 190x, and then plus 0. Yeah, plus 0. Okay. And so we're going to change the sign and add. Change the sign. Okay, and add. And we're going to get 87x squared. Oops, 87x squared. Come on. 87x squared plus 190x. Okay, plus 1. Okay, and that's our remainder. So the idea here, okay, is that this thing becomes plus 87x squared plus 190x plus 1 all over, okay, x cubed minus 3x squared minus 10x. Okay. Now we're going to integrate this whole thing. So we just did long division, and now we want to integrate the whole thing. Okay. Okay, so let's integrate this. Let's take the integral of x squared plus 3x plus 19 plus 87x squared plus 190x plus 1 all over x cubed minus 3x squared minus 10x, right? Okay. Okay, dx. Okay, so the first part of this is pretty easy to integrate. It's the last part that's going to be not too fun. Okay, so when I factor the denominator here, okay, when I factor the denominator, I get 87 x squared plus 190x plus 1 over, okay, x times, this is going to be x minus 5 times x plus 2. Okay, so this ends up being a partial fraction decomposition. Okay, and we get x squared plus 3x plus 19 plus this guy. Okay, so we want to do our partial fraction decomposition on the latter portion of this, on this rational function here. Okay, so we're going to say 87x squared plus 190x plus 1 is equal to a over x plus b over x minus 5 plus c over x plus 2. Now we're going to use a Heaviside technique on this, and that's to multiply through by the denominator. Okay, so this is all over x times x minus 5 times x plus 2, and I'm going to multiply through by our denominator. Okay, our denominator is going to get multiplied through. We're going to multiply through by x times x minus 5 times x plus 2. Oops. X plus 2, and so this is x times x minus 5 times x plus 2. That's just going to cancel the denominator there. And we're going to get 87x squared plus 190x plus 1 is equal to, this is going to be a times x minus 5 times x plus 2 plus b times bx times x plus 2 plus c times x minus 5. Okay, so now we've got 3 linear factors, which is nice. Okay, that's going to allow us to do some nice things here. Okay, and so just move up for me. Thank you. Okay. So we're going to let, first, let's let x equal 0. Let's let x equal 0. And so you can see on the left side, the whole thing is going to go to 1. On the right side, the b and the c are going to go to 0. And so I'm just left with a times negative 5 times 2. And so this implies that a is equal to 1 over negative 10. Okay, let's next let x equal 5, and that's going to allow me to get b. Okay, let x equal 5. That's going to allow me to get b. So we've got 87 times 5 squared plus 190 times 5. Okay, plus 1 is equal to, a and c are gone because that's going to just create zeros. B times 5 times 7, okay, or 35b. Okay, so we can figure out what the left side is here by just plugging it into a calculator. This is going to be equal to 37b, or 35b, sorry. 35b. Okay. I don't know if my calculator is going to come up or not. Let's see. I just want 87 times 5 squared plus 190 times 5 plus 1. Okay, so 87 times 5 squared. Oops. Okay, 87 times 5 squared plus 190 times 5. That didn't work. let me just clear the whole thing. Squared, okay, plus 190 times 5 squared, or 190 times 5. Keep forgetting the plus there. Plus. Okay, let me insert that plus sign. Okay, 190 times 5. And then that's is that a minus 1 or a plus 1? That's a plus 1. Plus 1. Okay, and I'm getting 3126, which is good. Okay, so is there a question here? Running down each section, trying my best to study it, lol, practice wrong. Okay, so 3126. Okay. So let's, I'm gonna move this over here. Let me minimize that in case I need it again. Okay, so we've got 3126 times 35, r is equal to 35b. So b, this implies that b is equal to 3126 over 35. Okay, now let's let x equal -2. Okay, let x equal -2. This is going to be 87 times -2 squared plus 190 times -2. Okay, plus 1 is equal to, okay, c, because the only one that's going to survive here is c. C times -2 times -7. C times -2 times -7. Okay, if I plug that all into a calculator, I get the following. I get -31 is equal to 14c. Excuse me. My water. Okay. Okay, so this implies that c is equal to -31 over 14. Okay. Okay, so we have all the pieces of the puzzle that we really need to solve this. Okay, so we want the integral now of x squared plus 3x plus 19 plus a over, okay, a over x plus b over x minus 5 plus c over x plus 2 dx. I'm just going to plug in my a, b, and c. So this is the integral of x squared plus 3x plus 19 plus, what do we say a was? A was my -1 over 10. So this is -1 over 10x plus what's b? B is my 3126 over 35. So this is 3126 over 35 times x minus 5 plus, or minus in this case, c is negative. So minus 31 over 14 times x plus 2 dx. Okay, so now let's integrate. Okay, we have everything we need to integrate. So this is going to be x cubed over 3 plus 3 halves x squared plus 19x minus 1/10 natural log of x plus 3126 over 35 natural log of x minus 5 minus 31 over 14 natural log of x plus 2. Okay, and I'm skipping the u to u substitutions on this simply because whenever when I take the derivative of x minus 5, that's the same as the derivative of x. Okay, the minus 5 is just a constant. It doesn't really play into the whole thing. Okay, yes, thank you, Ravi. Plus c. Okay, and that's my answer. Okay, so a pretty long problem. Okay, pretty long problem. I don't think I'd give you anything that long on the exam. But again, we want to do hard problems so that the easy problems are that much easier. Yeah, I think I have to recheck that. Oh, but yeah, I'm pretty sure that that's the case. Okay, but they are very long problems. Partial fracts are long. Okay, let's do a couple more of these. Okay, number 4. Okay, these ones aren't as long, thank goodness. Okay, dx over x times the square root of natural log of x. Okay. Okay, so let's do a u sub on this. Okay, what do I want for my u sub? Well, I have a 1 over x, right? Don't I have a 1 over x already? 1 over x dx. So the derivative of natural log is 1 over x. So I could get my u du here really pretty easy if I just let u equal, I let my u equal natural log of x, right? Because we can then let du equal to this 1 over x dx. Okay. Okay, so I'm just going to have the radical 1 over the square root of u du. Okay, this thing ends up being the radical of u to the negative 1/2 du. And that's the integral of 1/2, right? U to the 1/2. The reciprocal of 1/2 is 2. So let's just integrate this. 2 u to the 1/2. Okay, plus c, but what was u? U was natural log of x. So 2 natural log of x to the 1/2 plus c. And we're going to get 2 times the square root of natural log of x plus c. Always leave things the way you find them. Okay, so a lot of math students don't understand that if you're given a fraction, leave it as a fraction. If you're given a percentage, leave it as a percentage. If you're given something as a square root, leave it as a square root, right? If you're given something as a rational exponent, then leave it as a rational exponent. Okay, basically leave your toys the way you found them. Okay. Okay. Let's do number 5 here. Okay, the integral of the square root of 1 minus x all over 1 plus x. Okay. Okay, I'd like to get this as a trig function. The only thing I have to do is manipulate it algebraically in order to do that. Okay, so this thing I'm gonna break up into the square root of 1 minus x all over the square root of 1 plus x. And I'd like to get this to be the difference of 2 squares. And so what I'm going to do is I'm going to multiply both top and bottom here by radical 1 minus x. And that's going to allow me to get a difference of 2 squares, and that's going to allow me to take some trigonometry. Okay, so this becomes, okay, well, this is square root of 1 minus x squared. Okay. Okay, all over, so those are going to cancel, all over the square root, okay, of 1 minus x squared. Okay, so I just multiply those together, and that's the difference of 2 squares. 1 minus x squared. Okay, so now this becomes the integral of 1 minus x all over the square root of 1 minus x squared. I'm dropping my dx's here, which I don't mean to do. Okay, so this is dx. Okay, now I'm going to split this up into two separate integrals. Okay, so this is going to be integral of 1 over the square root of 1 minus x squared dx minus, maybe I'll do a minus here. Do I want a minus? No, I want a plus. Just thinking ahead, because when I take the derivative, I'm going to get a minus. So I want the minuses to cancel out. So I want a plus here of negative x over the square root of 1 minus x squared. Okay. Okay, well, what's the first one here? Anybody know what that is? What's the integral of 1 over 1 minus x squared? It was in that list of integrals that I gave you. Okay, yeah, arc sine. Thank you, Martin. Okay, it is arc sine. So this is the arc sine of x plus, now this is going to be a u to u substitution, right? Because if I let u equal the denominator here, 1 minus x squared, then du is equal to negative 2x dx. Oh, okay, there's a dx there. I keep dropping my dx's. Okay, and so we get du over 2 is equal to negative x dx. Oh, okay. So this guy becomes the integral of 1 over u, oh sorry, square root of u, du over 2. Okay, so let's factor out that 1/2. Okay, this becomes u to the negative 1/2, very similar to what we've already done. Okay, in the previous problem, okay, du, right? And so this thing is going to get raised to the 1/2 power, u to the 1/2 power, and then it's going to be the reciprocal. Okay, or I could take this 1/2 on the outside and divide by 1/2. And that just goes away. It becomes 1. Okay, so then this becomes the arc sine of x plus, okay, u to the 1/2 plus c. But what is u? U was 1 minus x squared, right? So this is inverse sine of x plus the square root, well, let's do 1 minus x squared, right? That's the u, all raised to the 1/2 plus c. Okay, and then the arc sine of x plus the square root of 1 minus x squared plus c. Oh. Okay. Okay, and that's number 5. Okay, so that's all of 7.5. Okay, let me know if there's any questions on 7.5 before we jump into 7.7. Okay. I think so. Yeah, I think so. I think it's 10 problems this time. Again, I would have to stop my share and look at it. But they're all roughly the same length. Okay. Okay. Okay, let's jump into 7.7 here. Okay, 7.7 is approximate integration. Okay, so 7.7 is approximate integration. Okay, so let's talk about left endpoint approximation. Okay, so left endpoint approximation. Okay, so we have a function, and we want to approximate the area under the integral. And so let's say that this is our function here. It's a pretty bad function. Okay, say that this is our function. Okay. I don't like that. I don't like it. Let me get a thicker line. Let me get a black line here. Let's make this thicker. Okay. Gosh, I can never do the end here. Okay, there we go. There's the idea. Still don't like it. I'm gonna be here all day. Okay, whatever. There, that's good enough. Okay, so we want to do the approximate integration here. And so what we're gonna do is break this up into rectangles. Okay, we're gonna do rectangular integration. Okay, and so left endpoint approximation. Okay, so I'm going to use the left endpoint as the height of my rectangles. So if I break this up into, okay, we call this x of 0. Okay, I want 1, 2, 3. I want three equal divisions here. Okay, 1, 2, and 3. Okay, that's not too bad. Okay, it's not gonna be perfect. Okay, so this is x of 1, x of 2, x of 3, and x of 4. Okay, and so the left endpoint for each of these is going to be the height of my rectangle. Okay, the left endpoint is going to be the height of my rectangle. So if I get some rectangles here, then this is the height of that rectangle. That's the height of that rectangle. This is the height of this rectangle. And this is the height of this rectangle. This is called my left endpoint approximation. Okay. And so the height of these rectangles give me an approximate value for the function, and then the area under these rectangles give me an approximate value for the integral. Okay, so that's why it's called approximate integration. And so we say from a to b of f of x dx is approximately what we call Rn. This is our integration with respect to, okay, sorry, it's ln, my bad. This is my left-hand integration, ln, okay? And we say that this is equal to the summation of the rectangles of I equals 1, okay, to n, okay? So x of i's, okay, I equals, is it 1 to n or 0 to n? Oh yeah, it's 1 because I'll show you in a second. We take into account that we're going to start at 0. So we're only using 0, 1, 2, and 3, right? We don't use 4 for one of our values because they're all on the left. So this is going to be f of x sub I minus 1. Okay, so that's the height of the rectangles, and then delta x is the width of the rectangles. Okay. So very similar to what we talk about when we introduce integration, okay, the first time. Okay, we're saying we're going to let delta x go to 0, okay, and then that ends up being our dx. Okay, so we're just saying that this is a left endpoint approximation or a left-hand approximate integration. And then if we plug this in, this becomes f of x0 times delta x plus f of x1 times delta x, okay, plus f of x2 delta x plus f of x3 delta x, right? Because we go from 1 to 4, in this case, 1 to 4, because we only had four rectangles. If we go 1 to 4, we're going to subtract off 1 to get our index, and that's going to go 0, 1, 2, 3, and that's the height. That's the function evaluated at that point, at these points. Maybe I'll make my points bigger. Okay, at these points, these these endpoints, okay, these are all left endpoints. And so we sum that up, okay, and what we're going to do is we're going to eventually just factor out the delta x, because all the delta x's, that's the width, okay, this is the width, this is the height of the rectangle, is the f sub x0, okay, so maybe I'll write that down, okay, this is the height of the rectangle, and this is, okay, this is the width of the rectangle, okay, width of each rectangle. Each rectangle has to have a common width, okay. Well, what we can do is we could factor out the delta x, and we could just add up the heights. F of x0, f of x1, f of x2, f of x3, and then multiply by delta x. Okay. Okay. Okay, a right endpoint approximation. Okay, a right endpoint approximation looks like so. Okay, let's go with green on this one. Right endpoint approximation. Okay. Okay, it looks like so. So what does a right endpoint approximation look like? Well, we're going to go like this, and then we're going to have our point. Okay, and we're going to have our endpoint, and we're going to have a similar curve. Okay, and so in this case, we're using right endpoints. So let's create our four divisions. 1, 2, 3, 4. 1, 2, 3, 4, and then 5. Okay, so that one's a little bit off right there. Let me move that over just a hair. Okay, and so here we're going to use our right endpoints as the heights of our rectangles. Okay, we're going to use the right endpoints as the heights of our rectangles. And so when we look at this guy, we're going to get this. Well, maybe I'll use a different color. What color? Ah, I didn't mean to do that. Go back. Okay. So let's use black. Let's use black. So we're going to go like this, and then like so. Okay, that's my first rectangle. This is my second rectangle. This is my third rectangle, and this is my fourth rectangle. Okay, and so we're getting a different estimate. Okay, and this is called a right endpoint approximation. Okay, where here the integral from a to b of f of x dx is approximately r sub n. This is my right-hand approximation, which is equal to the summation of I equals 1 to n of f of x sub I this time. This time we don't start at 0, we start at 1, right, for our heights. Okay, times delta x. Okay. Okay. And so in our case, okay, okay, and I could do dot dot dots here if I wanted to. And the previous one plus dot dot dot. Okay, plus dot 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 dot. Okay. And so again, we're going to start with f sub 1 this time. Okay, this is equal to f sub x sub 1. Okay, f of x sub 1 times delta x plus f of x sub 2 times delta x. Okay, and plus f of x sub 3 delta x plus f of x sub 4 delta x plus dot 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 dot. Okay, and then we can factor out that delta x if we wanted to. F of x1 plus f of x2 plus f of x3 plus f of x4 plus dot 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 forever. Okay. Okay. And that's our right endpoint approximation. Let me Make this a little bit smaller. Okay, let's do a problem now using these approximations. Okay. Okay, number 1. Find the, okay, let me get my piece of paper to really be a piece of paper again. I keep zooming in and zooming out. I keep losing all this stuff. Okay, so number 1. Okay, find the left and right endpoint approximation. Approximation okay, of the integral 1 to 2 of 1 over x dx for n equals 5. Okay. For n equals 5, n is going to be, we're going to have five partitions here. Okay, 5 partitions. Okay, so we want to go from 1 to 2, okay, for 1 over x. Well, what does 1 over x look like? 1 over x is our hyperbolic, okay, rational function, right? Okay, oops. Let's go like this. Okay, that still doesn't look good. Okay, that's a little bit better. I still don't like it. I don't like it. Okay, I'm going back to this one. There. Let's just deal with this one. Okay. Now where's 1? 1 is right here. 1 1, right? So again, f of x is equal to 1 over x. Okay, where's 1 1? It's right there. We're wanting to go from 1 to 2, right? 1 to 2. Okay, so 1 to 2, and I want to divide this into five increments. Okay, so how am I going to do 5 increments here? Well, I'm just going to take and find delta x. Delta x is going to be b minus a over n. Okay, b minus a over n, that's going to be the increments that I'm going to use. So this is going to be 2 minus 1 over 5, which is delta x, which is 1/5, which is 0.2. Okay, so 2, 4, 6, 8. Who do we appreciate? The fifths, right? The fifths. Okay, 0.2, 0.4, 0.6, 0.8. Okay, so 0.2. So this is going to be 1.2, 1.4, 1.6, 1.8, and then 1. And that's what I'm going to use for my rectangles. Okay, so I want to find a right approximation and a left approximation. Okay, so let's do the left approximation first. Okay, so I need to let's do the left approximation. That's the summation of I equals 1 to 5 in this case. Okay, and I'm going to use 2 different colors. Let's do left in green actually. Okay, ln left is in green. Okay, so let's do a left approximation. Oops. Okay, so we're going to use these left endpoints to help us approximate. Okay. Okay, that's gonna, and look at that. That is gonna be an overestimate, right? That's gonna be an overestimate. Does that make sense why it's an overestimate? Because I've got, okay, it's over, right? We've got these little pieces here that are over, okay, where, okay, so that's gonna be an overestimate. But that's okay, we're gonna get pretty close. Yeah?
Oh, I don't know if you're here.
I'm working till 5:30.
What?
I'm working till 5:30.
Oh,
Okay. Okay, so ln is equal to, okay, the summation of I equals 1 to 5. Okay, I equals 1 to 5 of f sub x sub I minus 1. Okay, f sub x of I minus 1 times delta x. Okay, so let's look at what this one is. Okay, so what I'd like to do is I'd like to get these values. I'd like to get my f sub x as well. Let's look at it first. This is going to be, okay, when x0, right? So this is x0, this is x1, x2, x3, x4, and x5. Okay. Okay, so what's x0? Well, that's 1. That's 1, right? So x is 1 when at x0. x0 is 1. So I'm going to say, oh, okay, this is going to be f of x sub 0 delta x plus f of x sub 1 delta x, and I'm going to have to do this 5 times. Okay, plus f of x2 delta x plus f of x3 delta x plus f of x4 delta x. Okay, so I already know what my delta x is. My delta x is 0.2, so I can factor that out, 0.2. But what I don't know is my f of x sub 0, f of x of 1, f of x of 2. So I'm just going to write it like this. This is f of 1, right, because x sub 0 is 1. What's x sub 1? Isn't that just f of 1.2? Isn't that just the height of the function at 1.2? Sure, absolutely. Plus f of 1.4 plus f of 1.6 plus f of 1.8. Okay, and so this is equal to 0.2 times, and the function is just 1 over x. So this is 1 over 1 plus 1 over 1.2 plus 1 over 1.4 plus 1 over 1.6 plus 1 over 1.8. And if I put all of that into a calculator, I get this equal to 0.74565. Okay, which again I'm going to say is an overestimate. Okay, this is an overestimate. Okay, overestimate. Okay, let's compare this to let's get the right hand one. Did my screen freeze? Hopefully it didn't freeze. Let's see if we can bring it back to life. Oh, for whatever reason it closed out. Okay, let's look at overestimate. Okay, that's an overestimate. Now let's look at R1, Rn, R sub n. Okay, the right side. Let's do this one in blue. Okay, R sub n. Okay, we're going to let this be the left hand endpoint or the right hand endpoints. Okay, on the right side. So notice that this is the blue here. Okay, this is the blue. Okay, this is where am I at? This is blue. Okay, this is blue. And this is blue. And what is that going to be? Well, that's going to be a gross underestimate, right? That's going to be a gross underestimate. Okay, and so it's the same procedure as before. It's just I equals 1 to 5. But in this case, we're going to start instead of at 1, we're going to go to 1.2 to, okay, this is f of x of I. Okay. Okay, times delta x. Okay, and so we're going to use, this is 0.2 times f of 1.2 plus f of, we're going to start at x of 1 and go to 5, right? Okay, maybe I won't skip that step. F of x1 plus f of x2 plus f of x3. I just factored out the delta x, so that's okay with you. Okay, plus f of x sub 4 plus f of x sub 5, right? So now we're going to go and we're going to do the 0.2, which is the 1/5 for delta x. F of x sub 1 is equal to 1 over 1.2, right? Because it's just going to be 1.2. I'm going to start with the x sub 1, which is 1.2, and then plus 1 over 1.4 plus 1 over 1.6 plus 1 over 1.8 plus 1 over 2. Put that all into a calculator, and I get an underestimate of 0.6 45635. That's an underestimate. Okay, underestimate. Okay, that's an underestimate. Okay, and we could already figure out what the true answer is, but that's not the point here. Okay, and we'll compare that to what the true answer is. Okay, in a little bit when we talk about error bounds. Okay. Okay, what is the actual error on these? Okay, I mean, it's really easy to go 1 to 2, right, of 1 over x dx. Okay, well, what would be the integral of this thing? This would be negative 1 over x squared for 1 to 2, right? So we could just plug this in, okay, right? So is that right? Negative 1, okay, integrate. No, that's not right. I don't know what I'm doing. I'm differentiating. This is natural log. Okay, that's natural log of x, right? Okay, and so what is the natural log of x from 1 to 2? Okay, so I just want to compare it to the real thing, like what's the real deal? Okay, and so this is an approximation of natural log 2 minus natural log 1. But what is natural log 1? That's 0. And what's natural log 2? Remember, natural log 2 was at 0.693, and then it just kind of went on forever. And so you can see, oh yeah, 0.693 is in between these two. Okay, the left-hand one was an overestimate. The right-hand one was an underestimate, but it got us a boundary for this thing, right? So we said that the integral from 1 over 2 to 1 over x dx is bounded by 0.645635 and 0.745635. It's interesting that they both end in 35. Okay, it must have something to do with the nature of taking 1/5 here. Okay. Oh yeah, because all we did was subtract off 1, right? No, we subtracted off a 0.1, yeah, because this is going to be 1 over 1 point, yeah, makes sense. Okay, so they are going to be there, because the overestimate is a 1, but the underestimate is a 1/2, right? So we end up taking off 1/2, but when you multiply 1/2 times 0.2, you take off 0.1. So it works out. It works out that they would be very similar, just off by 0.1. Okay, but can we do better? Can we do better than these? Okay, can we do better? Okay, can we do better? Can we get closer to the actual value of natural log? Okay, when people were initially doing this, they didn't really understand, well, you know, oh, well, natural log was, you know, found natural log of 2 was this function or whatever. And so they ran all this stuff by hand and trying to approximate that natural log of 2 idea. Okay, so can we do better? Well, let's instead of using a right or a left, let's use a midpoint. Okay, let's use a midpoint. Okay, so let's look at what we call the midpoint rule. Okay, the midpoint rule for approximations. Okay, so we're going to say the integral from a to b of f of x dx is going to be approximately equal to the midpoint rule here, approximately equal to the midpoint rule, which is equal to delta x times f of the average of I, of the ith interval, okay, equals blah, blah, blah. Okay, I could write this as a sum if I really wanted to. How do I want to write? No, yeah, let's write this as a sum. Okay. So the ith interval, let's do m is equal to the sum of I equals 1 to n, okay, of this thing here, which is equal to, okay, delta x times f of x sub bar 1 plus f of x sub bar x bar sub 2, okay, plus k dot dot dot, plus all the way up to n, okay, f of x sub r n, okay, where delta x is equal to b minus a over n, just like it was before, okay, and x bar I is equal to 1/2 of xi minus 1 plus xi, okay, which is equal to the midpoint, okay, of xi minus 1 xi. Okay. Okay, so that's the midpoint rule. So we're going to use the midpoint, the middle value in each of the intervals. Okay. Okay, so let's do the same problem we just did, but let's use the midpoint rule this time. Okay, I'm going to call this number 2, but it really is just the same thing that we did before. Okay, use the midpoint rule to approximate the integral of 1 to 2 of 1 over x dx, okay, for n equals 5. Again, 5 subdivisions. Okay, let's use the midpoint rule on this one. Okay, so let's draw our graph. Okay, here's my graph of 1 over x. Okay, so let's let this be 1, 1. Okay, 1, 1, and then we're going to go out to 1, 2. Or sorry, 2, 1/2, 2, 1/2, yeah, 2, 1/2. Okay, and now I want to draw some rectangles. But how am I going to get my rectangles? Well, okay, I still need 5 subdivisions. 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5. That's good. Okay, but instead of using a right endpoint or a left endpoint, I'm going to use the midpoint. Okay, I'm going to use the midpoint here. Okay, so where's the midpoint? Well, the midpoint's right in the middle of each of these. Okay, maybe I'll zoom in on this. Midpoints, okay, in the middle. And so how's my rectangle going to look? It's going to look like this, and this, and this, and this, and this. Okay, those are going to give me my rectangles. Okay, this is still at 0.2, 0.4, 0.6, 0.8. Okay, but okay, and still delta x. What's delta x? Delta x is still 1/5, right? Okay, it's 1/5, which is 0.2. But now I need to figure out, well, what's the midpoint of each of these, right? So what's x bar 1 equal to? What's x bar 1? Well, x bar 1 is going to be equal to, okay, the average between 1.2 and 1, right? So this is 1.2, right? Maybe I could put some ones in here. 1.2, 1.4, 1.6, 1.8. Okay. Okay, so the average between 1.2 and 1 is just going to be 1.1. So this is going to be 1.1. This is going to be 1.3, 1.5, okay, 1.7, and 1.9. So x bar 2 is 1.3, x bar 3 is 1.5, x bar 4, these are bars, x bar 4 is 1.7, and x bar 5 is 1.9. Okay. Oops. Okay. Makes sense? So far, so good. Go away. Okay. So now we just want to get the area of our rectangles, right? So we just want to get the area of our rectangles here. Okay, so again, this is going to be delta x times my x bars. So this is f of x bar 1 plus f of x bar 2 plus f of x bar 3 plus f of x bar 4 plus f of x bar 5. Okay, so if we're going to use these, then this is going to be f of 1.1 plus f of 1.3 plus f of 1.5 plus f of 1.7 plus f of 1.9, okay, times delta x. And what was delta x? Delta x was 0.2, right? Okay, so what's this going to be? It's going to be 0.2 times 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9. Okay, and if I plug all of that into a calculator, I get the midpoint approximation of 0.691908. Ooh, look at that. That's pretty close. That's a lot more accurate. Okay, much more accurate. Okay. Okay, so that's the midpoint rule. Okay, so we did the left, okay, we did the right, and we did the midpoint. Now we're going to do one more. We're going to do one more that may or may not be more accurate. Sometimes it is, sometimes it isn't. Okay, it all depends. Okay, the midpoint rule could be more accurate than the trapezoidal rule, or the trapezoidal rule could be more accurate than a midpoint rule. It all depends on, okay, what the function is. But the midpoint rule and the trapezoidal rule are more accurate than the rectangular rules. Okay, the left and right rectangles. So midpoint gives me a good value there. Okay, so let's discuss the trapezoidal rule.
Before you move, do you mind going back to the list of your x sub 1, sub 2, and how you got 1.1, 1.3, 1.5, and so on?
Yeah, so I'm taking the average of the x values, right? So it's x bar 1. So what is x sub 0 here? X sub 0, right? So it even says up here in the trapezoidal rule here, it says x bar sub I is equal to the x ith minus 1 value plus the x ith value times 1/2. That's just an average. We're just taking the average. So the average between 1 and 1.2 is 1.1. So it would be x0, right? X0, I'm sorry, this is a plus, my bad. That should be a plus. That's not a minus. It should be, let's do the average here. This would be 1 plus 1.2, right? You take that, that's 2.2, divide by 2, you get 1.1. So this is x0 plus x sub 1 over 2, right? That gives me that guy. X sub 1 plus x sub 2 over 2 is going to give me the next guy. Okay, and so on and so forth.
Thank you.
Sure. Okay, so let's look at the next rule, which is the trapezoidal rule. Okay. 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 So going back to this guy here. Okay, we want to do 4 divisions on him. 1, 2, cut them in half, and then cut those in half, and we get 4 divisions, right? 4 divisions, okay? And so what I want to do is I want to look at these points, these values here, where we're at x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. Okay, and what I want to do is I want to create trapezoids. I just want to connect these dots with linear lines. Okay, so I want to create trapezoids. Okay, with the linear lines. That one's almost linear itself. Okay, so this is going to give me an approximate area based on trapezoids. Okay, trapezoids. So what we're trying to do is minimize the error on these, right? So trapezoids. So that's going to give me even less error than the rectangular rule, okay, of left rectangles and right rectangles. Okay, so this is the trapezoidal rule. Okay, so this we want the area of a trapezoid. The area of a trapezoid, okay, is equal to 1/2 base 1 plus base 2 times height, right? Okay, and in our case, it's going to be equal to 1/2 f sub x I minus 1 plus, okay, f sub x sub I times the height, okay, the height of the rectangle, the trapezoid is really delta x. Okay, the bases, if we look at this, okay, the height of the rectangle is right here. Or sorry, not the rectangle, the trapezoid. All right, let's look at the trapezoid here. This trapezoid, okay, the one that and if I were to flip that trapezoid on its side, then the height of the trapezoids are always the same. Always the same height. Each height is the same here for each of these trapezoids. Okay. So the height is the same, and then we're just going to use the height of the function as the basis of the trapezoid. Okay, the height of the function we're going to use as the basis of the trapezoids. Okay. Okay, and so then this is going to be delta x is the height there. Okay, and so we're going to take the base 1, right? So think of this as base 1, and then think of this guy as base 2, right? Base 1 is this guy here, base 1 and base 2, right? Base 1, base 2, and that's going to be the height of my function. Okay, on my two bases. Okay, so we're going to call this the trapezoid approximation, or T sub n is equal to 1/2 delta x. So I'm going to put that delta x in front. I'm going to go delta x over 2 times, okay, times f of x sub 0 plus f of x of 1, okay, f of x of 1, okay, plus, and then we're just going to keep doing this. This is the area of one trapezoid. What if I wanted the area of all trapezoids? Okay, area of one trapezoid is this thing. If I wanted the area of all trapezoids, I just have to go I equals 1 to n. Okay, sum them all up. Sum up all the trapezoids. Okay. T sub n. Okay, so then this is going to be plus delta x over 2 times, okay, f of, we're going to move on to the next trapezoid. So that's base 1 plus base, or base 2 plus base 3. So this is f of x1. We're going to change the bases that we're going to be working with. It's going to create the next trapezoid, plus f of x2, right? And so we go all the way up, okay, dot, 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 all the way up to n trapezoids, okay, n trapezoids. So 2, and then this is f sub n minus 1. This is x sub n minus 1, f of x sub n minus 1, plus f of x sub n. Okay. Okay, so now what I'm going to do is factor out that delta x, okay, and we're going to see a pattern here arise in that I only have one f of x sub 0. If I factor out the delta x over 2, I have one f of x sub 0, but I have 2 of everything else except for the x sub n. The endpoints here, the bread in the sandwich, okay, this guy here and this guy here, they don't have partners, but everything else does. Everything else has a partner there. And so this becomes 2 f of x1 plus 2 f of x2 to f of x2 plus blah, dot, 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 plus 2 of f of 2 of f of x sub n minus 1 plus 2 or plus f of x sub n. The bookends here, they don't have 2's, everything else does. This is f of x sub n minus 1. X sub n minus 1. Okay? Good stuff. And that is the trapezoidal rule. Okay, in a nutshell. Whatever that means. Okay, so guess what we're going to calculate now? Have any ideas? Any wild guesses? We're going to do natural log of 2. we're going to get this for 1 over x. Okay, and we're going to use the trapezoidal rule. Okay, so let's do the trapezoidal rule here. Okay, so we'll make this number 3. For 1 over 2 to 1 over x dx, for n equals 5, use trapezoidal rule to approximate. Okay, let's use the trapezoidal rule now to approximate this. Okay, cool. Okay, so let's draw a picture real quick. Okay, we've got our 1 over x going like this. Okay, let's get our 1, 1. Our 1, 1 is right here. Where's our 1, 2? Or sorry, our 2, 1/2. Our 2, 1/2 is about here. Okay, 2, 1/2. I'm going to zoom in on this. Okay. What the heck? It froze again. Oh, no, it didn't. Hello? Stop freezing on me. There we go. Okay. Okay, so I want n equals 5, so we've got to have 5 subdivisions here. 1, 2, 3, 4, and 5. Whoops, those aren't spaced evenly. Let's get rid of that. Okay, there we go. Erase that. Bring that back. Erase that. Erase that. Okay. Try to space these a little bit nicer. 1, 2, 3, 4. Okay, that's better. Okay, so we're going to have this guy, this guy, this guy, and this guy. Again, the trapezoids are going to be really hard to draw, but you're going to get the idea here. Okay, trapezoids, trapezoids, trapezoids. Okay, trapezoids for days. Trapezoids. Okay, we've got our trapezoids. Although I don't really like. Don't do that. My eraser is way too powerful. Okay. Okay, so we've got trapezoids going on all over the place. Okay. Okay. So now let's figure out what we have here. We have x of 0. Is this on my thing? This is zoomed way in. X of 0, x of 1, x of 2, x of 3, x of 4, and x of 5, right? Okay. So how are we going to find our bases, right, at these? Well, this is from 1 to 2, right? So this is 1.2, 1.4, 1.6, 1.8, and 2. And so, again, what's the trapezoidal rule say? It says delta x over 2 times f of, okay, f of x sub 0 plus 2 of f of x sub 1s, okay, plus 2 of f of x sub 2s, plus 2 of f of x sub 3s, plus 2 of f of x sub 4s, plus 1 of f of x sub 5s. Oh, okay. Okay. Okay, so this is going to be, what's delta x? Well, delta x in this case is 0.2, right? So this is 0.2 over 2, okay, 0.2 over 2, which is 0.1, times, okay, f of x of 0. Okay, well, what's f of x of 0? That's going to be f of 1. F of 1 plus 2 times, this is going to be f of 1.2 plus 2 of f of 1.4 plus 2 of f of 1.6 plus 2 of f of 1.8 plus f of 2.0. Okay, so this is going to be 1 over 1 plus 2 over 1.2 plus 2 1.4 plus 2 over 1.6 plus 2 over 1.8 plus 2 over 2. Okay. If you plug all of that into a calculator, you'll get an approximate answer. Oh, this is not 2, I'm sorry. This is 1. I got carried away there. This is 1 over 2. Okay, because there's only one f of 2. And remember, what's f of x? F of x is 1 over x, right? So f of x is 1 over x. So, yeah. So this is equal to 0.695635. Okay. Okay. So the midpoint rule, okay, this is the trapezoidal rule, t of basically 5, t sub 5, erase, darn it. Okay, so t sub 5 is equal to this. Okay, m sub 5, what was m sub 5? M sub 5 was 0.691 something. It was 0.691908. 691,908. Okay, that was the midpoint rule, right? And the actual value of natural log of 2 is equal to 0.693147. Okay. Okay, dot goes on forever. Okay. So do these. I'm just rounding everything to 6 decimal places. Okay. Okay. So I want to know, well, what is this? This is obviously an overestimate for the trapezoidal rule and an underestimate for the midpoint rule, but it's much better than the over and under that we got for the rectangulars, right? What was the rectangulars again? Let's look back here. What was L, right? What was L sub 5? L sub 5 was equal to 0.745635. This is 0.745635. Okay. And R sub 5 is equal to 0.645635. Remember, they were off by 0.1. Okay, this is a gross overestimate. Grossly over. Okay. And this is grossly under. Okay. Grossly over and grossly under. Okay. So we can see that even though the trapezoidal was over, it wasn't over by a whole lot, and the midpoint was under. Well, how can we get our error? Well, our error on any of these is just, okay, is just taking the approximation, we have the approximation, okay, minus the actual integral, okay, and then that's the absolute value, and this is going to give us our error. Okay, it's the approximation minus the actual value of the integral, and that gives us our error. Okay, gives us our error here. Okay, so let's look at the midpoint error. Okay, the M5 error. Okay, well, that's just going to be 6.691908 minus 0.693147 absolute value, and that's going to be 0.001239. Okay, so the error on the midpoint was 0.001239. Okay. Okay, so what about the trapezoidal rule error? Okay, that's going to be 0.695635 minus 0.693147. Oops, absolute value. Okay, and that equals 0.002 488, almost twice the error. 488. Okay, about twice the error there. Okay, so the trapezoidal. So this one, the midpoint rule was the best to go with. This is the best to go with for this function. Okay, that's not always the case, but for this function, the midpoint rule was the best approximation. Best approximation. Okay. Okay, let's talk a little bit about error bounds. Okay, before that, I need to go get some more drink because my mouth is getting parched. I'll be right back. Okay, I'm back. I had to get some more lemonade. Keep me going here. Okay, let's look at the error bounds here. Okay, so suppose, I need to actually zoom out here. Suppose that my eraser works. Is somebody not muted? Okay, suppose I'm going to stop my share real quick and then reshare because it's lagging for me. Okay. Okay, let me go back to my screen share. Share my screen. Okay, so error bounds. Okay, that's much better. Okay, suppose that the absolute value of f double prime of x is less than or equal to k for all x between a and b. Oops. And the error of the trapezoid and the error of the midpoint, okay, are the errors E sub t and E sub m. Okay, maybe I'll write that over here. Okay, E sub t, nope, that was the m, right? That was the m. E sub m, and then E sub t, there we go. Okay, E sub t and E sub m are the errors in the trapezoidal rule and the trapezoidal and midpoint rules, respectively. Okay, then we can approximate the error without actually having to calculate it fully out. Okay, if we say we just want the error, well, we want to bound on the error. What's an upper bound for the error? Then, okay, we can take this second derivative absolute value, and we're going to say that's less than or equal to k. Then the error for the trapezoidal, okay, is less than or equal to k times b minus a squared over 12n squared. That's for the trapezoidal rule. Okay, and okay, for the midpoint rule, we can get an error bound okay, k of b minus a cubed over 24n squared, okay, provide upper bounds on these errors. Okay, this provides upper bounds on these errors. Okay. Okay. So let's work with these errors real quick. Okay. Okay. So let's go back to our friend. Okay, 1 over x. Okay, the integral of 1 to 2 of 1 over x dx. Okay. Let's find the error bound for the trapezoidal rule. Okay, let's find an error bound for the trapezoidal rule. Okay, so this is the upper error bound. We just want to know in the ballpark, what's this error going to be? Okay, can we restrict it a certain amount? Okay, where n equals 5. Okay, find the error bound, or find a bound. Let's not the bound. Find a bound for e of t. Okay, the error of the trapezoidal. Okay, what will be the error of the trapezoidal here? Okay, so we're going to want to find the second derivative of this. We want to find the absolute value of the second derivative, okay, of x, right? Okay, is less than k. Okay, was less than or equal to k. Okay, so if f of x is equal to 1 over x, then f prime of x is equal to x to the negative first power. And then f prime of x is negative 1 times x to the negative second power. Okay, and f triple prime of x is going to be 2x to the negative third power, which is equal to 2 over x cubed. Okay, so the error bound on this, okay, less than or equal to k. K is just a value that I want to figure out. Well, what is this going to be less than or equal to in my region, right? Because again, x goes from 1 to 2, right? X goes from 1 to 2. Okay, and so what's going to be my upper bound on f prime of x? F prime of x, I want to know what's going to be my upper bound is less than or equal to some k value, right? Okay, so we can think of this as, okay, what's the f double prime of 1 and what's f double prime of 2, right? Let's think of that. And what we want is the bigger one. We want to take the bigger one of these, not the smaller one. We want the upper bound. We want k to be, we want all of the f primes to be less than or equal to some value. So if I take and evaluate f double prime of 1, I'm going to get 2 over 1 cubed, which is 2. And if I take f double prime, I'm going to get 2 over 2 cubed, which is 1/4. So which one's bigger here? Well, it's the one that involves the 1 here. So we know that f double prime of x in our region is less than or equal to 2. That's going to be equal to k. Oh, okay. So what's the error? Okay, what's the error here? The absolute value of the error. Did I put absolute value on the errors? Yeah, I did. Okay, the absolute value of the error of t, okay, is equal to k times b minus a all over, or b minus a squared all over 12n. Okay, 12n, is it squared? Go back here. Okay, yeah, 12n squared. Okay. Put that out of my notes. 12n squared. Okay. Okay, so k is going to be equal to 2, okay, times b minus a. Well, that's just 2 minus 1 squared. That's just going to be 1. all over 12 times n. Well, how many divisions were there? There were 5 divisions. Okay. So this is going to be equal to 2 over, this actually is 6, right? So it's going to be 2 minus 1, which is 1. So 1 squared is 1. Okay, 6 times 25 is 150. So this becomes 1 over 150. Okay, which is approximately 0.00667. Okay, it's basically 0.006 repeated forever, but I want to go out 6 decimal places. Why do I want to go out 6 decimal places? Because I want to compare that to the error that we got. So E of t, okay, we're going to say is less than or equal to, okay, less than or equal to, the error of t is less than or equal to 0.006, okay, 667, okay. And so how does this compare to the actual error? The actual error. Well, the actual error, remember, was 0.002488. Okay, the actual error was 0.002488, which is within this boundary. This is an upper bound. Remember, this is just a guess. It's an educated guess. Okay, it tells us, oh, okay, so the error is pretty small. The actual error is 1/3 as much, but I mean, we're still to the, what, thousandths place, three thousandths? I mean, it's still pretty accurate. Okay, so compared to the actual error, this is the actual error compared to 0.006667. This is the estimated error. Okay. And we could do the exact same thing with the midpoint, right? We could do the exact same thing with the midpoint. If we want to do the midpoint, right? The midpoint was what? What was the midpoint formula here? It was k times, okay, b minus a cubed all over 24 this time, 24n squared. Well, k is going to be the exact same thing that we got before, okay, which is basically all I'm going to do is cut this thing in half, the estimated error, but we'll get there. Okay. Is it 12n or is it 12n squared? I'm confused. No, it should be n squared. Yeah, 12n squared. Yeah. Okay, no, it's fine. Okay, so 24n squared. So this is going to be 2 again because we already did all of our second derivatives. Times 2 minus 1 cubed all over 24 this time. So this is going to be 1/12 times 5 squared. So this is just going to be, instead of 150, this is going to be 1 over 300. Okay, which is going to end up being 0.0033 forever. Okay, 0.003333 forever. Okay, so how did that compare to our midpoint? Well, 0.003333 is less than or equal to our midpoint. Okay, our midpoint error, this is backwards. Our actual midpoint error was 0.001239, and that is less than or equal to our estimate of 0.00333. Okay, so this is our actual error. This is our estimated error. So again, it just gives us a ballpark to work in for these errors. Okay. Let's look at another one here. Okay, man, I ran out of paper again. Did I run out of paper? I think I did. I did run out of paper. Okay, yeah, I did run out of paper. A lot. let me insert some more paper here because we've got a little more ways to go. Okay, that's what happens when you lecture for 3 hours straight. You run out of paper. Okay. Let me insert some more blank pages here. Blank pages, open. It's a stretch break. Stretch break. Maybe we'll take a little stretch break. Okay. Stretch. Stretch. Ooh. Okay. Okay, better. Come on, are you gonna insert any day now? I'm gonna stop my share so this goes faster. I just wanted to insert some paper. Could you just please insert my paper? Thank you. Thank you, thank you, thank you. Come on. Let's try this again. Okay. Well, this is fun. I might just not put in the paper, actually. It's taking forever in a day. Okay, forget it. We'll just keep going with this thing. Okay, let's talk about Simpson's rule real quick. Okay. Simpson's rule. Okay, and this is based on parabolas. Okay, so this is based on parabolas between the points. So each of these gets increasingly more and more complex.
Professor, we cannot see your screen.
Oh, thank you, thank you, thank you. Okay. Yes, I forgot. I stopped sharing. Okay, Simpson's rule. Okay, so this they become increasingly more and more complex, but it's all good. Okay, this is based on parabolas between points, based on parabolas between the points. Okay, instead of trapezoids or rectangles or straight lines, instead of straight lines for midpoint for all of the other ones, okay, even the trapezoid was a straight line. This is based on a parabola, a curve, okay, between the points. So we're going to say that the integral from a to b of f of x dx is approximately, okay, s of n for Simpson's rule, which is delta x over 3, okay, times, okay, f of x sub 0 plus 4, and then we get this alternating pattern here, 4, 2, 4, 2, 4, 2. Okay, 4 f of x sub 1 plus 2 f of x sub 2 plus 4 f of x sub 3 okay, plus dot, plus 2, okay, 2 f of x sub n minus 2 plus 4 f of x sub n minus 1. Oops. How am I doing this? Let's get the parentheses correct. 4 f of x plus, and the very last one, f of x sub n, does not have any. Okay, very similar to the trapezoidal rule, but instead of 2's, we're doing this alternating 4-2, 4-2 pattern. Okay, 4-2, 4-2 pattern. Okay, where n is even. We have to have an even n though. That's the caveat here. Where n is even, we have to have an even amount of subdivisions where n is even, and okay, delta x is equal to b minus a over n. Again, same thing as before. Okay. Okay, so that's Simpson's rule. Okay. So number 5 here, let's use Simpson's rule with n equals 10. Okay, so not 5 anymore, n equals 10, to approximate okay, the integral from 1 to 2 of 1 over x dx. Okay, our same natural log. Okay, derivative integral. Okay, dx. Okay, so delta x in this case, okay, is going to be equal to b minus a over n, right? So this is going to be 2 minus 1 over 10, which is 1/10. Okay, so these are going to be in 0.1s. Okay, so f of x sub 0, okay, this is going to go x sub 0 all the way to x sub 10. Okay, f of x sub 0, f of x sub 1, f of x sub 2, f of x sub 3, f of x sub 4, f of x sub 5, f of x sub 6, f of x sub 7, f of x sub 8, f of x sub 9, f of x sub 10. These are kind of off, but whatever. You get the idea. Okay, so what's this going to be? This is going to be f of 1, right? And then we're going to go up by 0.1s, right? 0.1s. Okay, this is going to be f of 1.1, f of 1.2, f of 1.3, f of 1.4, f of 1.5, okay, f of 1.6, f of 1.7, f of 1.8, f of 1.9, and f of 2.0. Okay, so now we have an even amount of, n is an even amount. And so we get an odd amount of values here, which is what we want. Okay, so we can use our Simpson's rule. Okay, so what is S sub n? S sub n is going to be equal to delta x over 3, okay, or that 0.1 over 3, times what? Times f of 1, plus, and we're going to go to a 4 first, 4 times f of 1.1, then we're going to go to 2, f of 1.2, then we're going to go back to a 4, 1.3, oops, forgot my f of 1.3, then we're going to go back to a 2, f of 1.4, then we're going to go back to a 4, right? Let me move this over. Okay, then we're going to go back to a 4 times f of 1.5. Then I'm going to go back to a 2, f of 1.6. Then I'm going to go back to a 4, f of 1.7. Then I'm going to go back to a 2, f of 1.8. And I'm going to go back to a 4. we want to start on a 4 and we want to end on a 4. That's why we needed an even number of intervals, but it gives us an odd number of terms. Okay, so we can get this kind of bookends here. 4 times f of 1.9 plus, and then the bookends do not have any coefficients, so this is f of 2. Okay. Okay, so what's delta x? Well, that's 0.1 over 3, right? And then what's f sub 1? Well, f sub 1 was just 1 over 1. This is 1 over 1.1. This is 1 over 1.2, and then so on, right? This is 1 over 2. Okay, and so this is going to be 1 over 1, which is 1, okay, plus 4 over 1.1, plus 2 over 1.2, plus 4 over 1.3, plus 2 over 1.4, plus 4 over 1.5, plus 2 over 1.6, plus 4 over 1.7, plus 2 over 1.8, plus 4 over 1.9, plus 1 over 2. Boom, that's a lot. That's a mouthful. Okay. Okay, if I plug all of that into a calculator, which, you know, just make sure that you plug it in correctly, I would come out with this bad boy here, 0.693150. Look at that. That's craziness right there. Okay. Again, let's compare to our actual value. Again, compare to, okay, 0.693147, which is the actual value, which is the actual value. Okay, so how does this compare? Well, it's dang close. That's all I can say. Okay, it's dang close. Okay, how close is it? Well, let's look at the error. The error for Simpson's rule here, okay, is equal to 0.693150 minus 0.693147 is equal to 0.0000. How many zeros do we have here? 1, 2, 3, 4, 5. 5 zeros into 3, right? Okay, it's within 3 tenths, hundreds, thousands, 10,000s, 100,000s, millions. It's within 3 millionths. Okay, that's pretty darn close. Okay, within 3 millionths. Okay, so let's look at the error-bound formula for Simpson's rule. There is an error-bound formula. Okay, this is the actual error. Is there a way to estimate the error for Simpson's rule? And it is. Okay, the estimated error for Simpson's rule, okay, is absolute value E of S is less or equal to K times B minus A to the 5th power all over 180 n to the 4th, where K this time is the 4th derivative, not the 2nd. We've got to take 4 derivatives this time, where K is the upper bound of the 4th derivative, okay, of X for less than or equal to K. Okay, for X going from A to B. Okay, so that's the error bound. Okay, the upper bound on my error. So let's go ahead and calculate that. Right? What is the upper bound on my error? Okay, for this one. Okay, what is the upper bound on the error for this one? Okay, so let's look at K in this case. So this is going to be f of X, okay, is equal to, okay, find estimated error of the integral of 1 to 2 of 1 over x dx for n is equal to 10 this time, of Simpson's rule. Of the Simpson's rule approximation. Okay, Simpson's rule approximation. Okay, so let's see how we can do this one. So f of x is equal to 1 over x, right, which is equal to x to the negative 1 power. So I want to take 4 derivatives of this. I want to do f prime of x is equal to negative x to the negative 2. F double prime of x is equal to 2x to the negative 3. F triple prime of x is equal to negative 6x to the negative 4. And f, the fourth derivative of f, is equal to 24 x to the negative 5th, which is just 24 over x to the 5th. Okay. And then we're going to look at 1 is less than or equal to x, which is less than or equal to 2. So in this case, again, what's going to be my upper bound? Well, it's when I plug in the lowest number because I'm dividing, right? When we divide by a smaller number, we get a bigger value. So I'm going to divide by that 1, and so my k ends up being 24 in this case. Okay, k is equal to 24. Okay, and so the error for Simpson's rule is going to be bounded, okay, is going to be bounded by, is going to be less than or equal to, oh yeah, these are all less than, okay. Yeah, it's going to be less than or equal to, okay, 24 times, and what was the rule here? It was b minus a, well, that's an easy one, 2 minus 1 to the 5th power, that's just 1, all over 180 times n to the 4th, well, that's 10 to the 4th power. Okay. Okay, and what does this equal? This equals 24, 180. How many times does 24 go into 180? Does it go in? Let me bring up my calculator here. Let me calculate this bad boy. Come on, you didn't. Okay, so I'm going to go I'm going to go 24, 180 divided by 24. Does that go in? Okay, 7.5. Okay, so it really doesn't go in evenly, but if I would divide both top and bottom by 12, I would get 2 over 15, right? So this is going to be 2, that's 15. Okay, so this is 2 over, and this is 15 times 10 to the 4. Well, 10 to the 4 is 10,000. So this is 15 times 10,000, which is 150,000, I believe. Let me check with my calculator. Okay, so 215, let's do 180. Oops, let's clear this. Let's do 15 times 10 raised to the 4th power. K is 150,000. So 2 divided by 150,000, okay, is roughly, okay, 0.0000, 4 zeros, 1 3, okay, forever. Okay, yeah. Okay, so we've got 4 zeros, 1 3 forever. Okay, and so this gives me an upper bound. because the actual, what was the actual again? The actual error was 0.00012345503, which is less than or equal to this upper bound of 0.0000013 forever. Okay, so this one has 5 zeros. This is the actual error. And this one has 6 zeros, or 4 zeros. Okay, this is the estimated error, so it is bigger. Okay, so that is bigger. Okay, let's do one more problem here. I'm going to call this problem number 6. Okay, find n such that the Simpsons rule, so we're going to do the last problem, but we're going to do it backwards, such that the Simpsons rule error is less than 0.0001 for 1 to 2, 1 over x dx. Okay, so what this is saying is I want the error of my Simpsons rule to be less than 0.0001. Okay, so how many, what does n have to be within this bound? Okay, we got, in the last one, we got less than 0.0013, and that was when we used 10. So what do we have to use to be within less of an error bound? Okay, 1/10 the size of the error bound here. Okay, or 10 times larger error bound than what we got before when we used n equals 10. Okay, I would assume that this is going to be less, less divisions. Okay, the more divisions you get, the better your approximation, right? Okay, so again, we want to say, well we want to do E sub s, okay, is less than or equal to k times b minus a to the 5th all over 180 n to the 4th. Okay, and I want that less than 0.0001. Okay, well, we already calculated this thing out. This was 24, right? 24, and this was 1 to the 5th, okay, all over 180 times n to the 4th. What we're doing now is we don't know what n is this time, and so we're just going to calculate out what n is. Okay, so this is going to be, I could multiply by 180 over 24, okay, on both sides. Okay, I may want to, in this case, I may want to flip things upside down first. Let's make this a fraction. This is 1 out of 10,000, right? And not 1 out over 10,000. Tenths, hundredths, thousandths, 10,000ths. So this is going to be 24 over 180. Okay, n to the 4th. And then I'm going to flip these upside down. Does anybody know what happens to the inequality when I flip fractions upside down? Yeah, the inequality sign flips. So this is going to be 180, okay, 180 n to the 4th over 24 is greater than 10,000. Okay, greater than 10,000. Okay. So now let's multiply both sides by 24 over 180. Okay, so multiply both sides by 24 over 180. What did we find that out to be? We found that out to be 2/15, I believe, right? Is that right? 2/15. Okay. So that just cancels. And we get n to the 4th power is greater than 20,000 over 15. Oh, okay. So now I'm just going to take the 4th root of both sides. Okay. Of this 20,000 over 15, right? Okay. Did I do that right? I think so. Okay, and what do I get? Let me plug this into the calculator and see what we get here. Okay, what's 20,000 divided by 15? Okay, is that thing, and then I want the 4th root of this thing. So raised to the 0.25 power, and I get 6. Yes, that's exactly the answer. I get 6.04. So n is greater than 6.04. Okay, so what is n? N can't be 6. Okay, n cannot be 6. It also cannot be 7. So n cannot equal 6 and n cannot equal 7. Why can it not equal 7? Why can n not equal 7? It can't equal 6 because it's too small. But why can n not equal 7? Why does n have to jump to 8? Because it's the nature of the Simpsons rule. What? Say it again? It has to be
And
even.
can be odd.
Yeah, it can't be odd. It has to be even. It's the nature of Simpsons rule. It has to be even. So n is equal to 8. Okay, it must be even and 6 is too low. Okay? Okay, that's it for today. Okay, we're done. That was a lot of material. Okay, every day is a lot of material.
Professor, can you move up to number 5? I missed a little bit.
Number 5? Sure.
Yeah.
Okay, there's number 5. Okay, see you later.
All right, I got it. Thank you so much.
Okay, sure. You're welcome.